All right, physics notes 9.1 to 9.4 and unit 9.6. This is part B. So we're going to do questions 4, 5, 6, and 7, applying the concepts of equilibrium using torque and F net equals ma, or F net equals 0, and using the idea of the center of gravity of an object being placed all at one spot. And here we have a problem kind of like the one we in number 3, but now we have a board, a teeter-totter, that does have a weight. And in the diagram, they have D for distance. I'm going to call that R. I'm going to go back down over here. This is going to be R1 and R2. R1 and R2. And we have two people, kids, I guess, sitting at the end of a teeter-totter. Teeter-totter is 3.0 meters long. And it's going to ask you where the fulcrum should be put, this balance point here in the center. And that's where it's going to rotate around. So we want this balance, so people could sit in equilibrium, and they're not going up or down unless they push with their legs, which we don't want to do. So the diagram is you draw the teeter-totter sideways. And by the way, there could be problems where you have a vertical object, and then you would draw the forces left and right. Like say you have a telephone pole, and you have like the wind and other forces blowing on it, or people pushing on it left and right. So those are not as common because you really don't put the weight into those problems, because the weight acts up and down. So most of the problems we're doing here are problems like this with including weight vectors, because that's usually the way we experience torque, because weight is a contributor. It's a force on the lever that makes things rotate. We'll see more examples. But the concept or the strategy, once again, is to draw your lever as a horizontal line or whatever orientation it has. There are actually some that are at angles too. Once again, we'll do one kind of like that at the end. But put all the forces, all the weights on there. Now, over here at this right end, all right, they have it labeled as M2G, but it tells you in this case that M2 is 28. So I'm going to do that in my head. It's 280 newtons. That'll be close enough. At the other end, we have the heavier person, 380 newtons. I'm getting that from the information given. Person number 1 is 38 kilograms times 10, 380 newtons. Now, it's pretty obvious here at the fulcrum, so that's a term that I haven't used yet. That's where there's an obvious balance point, and there wasn't an obvious fulcrum on the other problem with the diving board. And you can, once again, you can kind of treat almost any spot as the fulcrum in a loose sense. But here, this one's obviously a pivot point, so it's more common to call that the fulcrum. It's obvious that that's where the rotation is. But there's a normal force, and we can call it F sub n. F sub n, it's a support force there. That's pretty obvious, going to hold the board up. But now it says the board itself has a mass of 45 kilograms. And it says it's a uniform board, uniform teeter-totter. And we have to factor that mass, more specifically, that weight into the problem. Well, 45 kilograms is 450 newtons. And the idea here is we're going to put all the weight of the teeter-totter, when it's a uniform object, a uniform rigid object, we put all the weight right there at its center of gravity. That's halfway between the two ends. All right? That's a big force. That's 450, and I have these somewhat to scale here. 450 newtons. It's the biggest force down. So the two kids are applying downward forces. The weight of the board is down. And once again, the weight of the board is all spread out, but we're treating the board like one. But we're still going to put the board as a 3-meter board, but all its weight in the center. And here's where the support force is. Now, this is a case where the second condition, or whatever you want to call it, the second or first condition of equilibrium is easy. The F net equals 0. All right, hopefully you can see this. If there's only 4 forces acting, F net equals 0. I'll do that over to the left here. F net equals 0. In other words, the forces up have to equal the forces down. Or in other words, forces up plus forces down equals 0 in a sense, but basically you're subtracting them. Well, it's just easy to write it down like this. Force up equals force down. Well, we have only one force up. Fn. F sub n, the normal force, equals 380 plus 450 plus 280. So the normal force here is 1,100 newtons up. 1,100 newtons up. We already know it's up. So I would just, if you just put 1,100 newtons, I would take it. That's just adding those three numbers together. Hopefully I did that correctly. I rounded off to 2 sig figs. Okay. You actually could have gone to 3 sig figs on that one. The second condition now, the torque net equals 0. Torque net equals 0. So you don't have to write this down, but torque net equals 0. Well, you don't need to write that statement down, but what you do want to do is, well, find your reference point. In this case, I'm going to mix it up a little bit. Here's the thing. It turns out that if you put your point A, your reference point, far to the left, it works out pretty well. You can put your reference point here at far to the left, okay, at point A, point B, point C, or point D. Any of those 4 points. It turns out that point B is the worst point to pick. You can try it yourself, but what you're going to find out is point B is the hardest point to use to apply the torque equilibrium condition. The main reason why point B is difficult to pick, even though it's the actual fulcrum, is you don't know where it's at. You don't know where it's located, so you get a bunch of unknown distances. And the problem becomes very difficult algebraically. I just want to show you again. So I'm gonna pick point D. All right, point D. Far right. But points A and C would also work pretty well here. Point B makes the problem very difficult. And you'll sort of see why. You already know, hopefully, well, you've read the question, or you can look back, that this distance right here is 1.5 meters. Right, 1.5 meters, because it says the board is 3 meters long, and that's point C is the center of gravity of the board. And this is 1.5 meters, total distance of 3 meters. And what we're going to be doing is we're going to be measuring everything from point D, because I'm going to use point D as my reference point. So whenever you pick your reference point, you got to measure everything from there. So I know from D to C is 1.5. From D to A is 3 meters. But from D to B is the only thing that's unknown. That's what we're actually looking for there. All right. Now in the problem over there, it says that's D2. I'm going to call that R2. Or you can just call it R. It doesn't really matter. Okay. But that they have R2 here in the diagram. You could call it R. Because once we know that, say it's 2 meters, then A to B is 1 meter, because I know the whole board is 3 meters. Getting ahead of myself again a little bit here. But I want to apply torque net equals 0 from point D. So the condition is, I always write this down, that the clockwise torque is equal to the counterclockwise torque. But here's where the thinking has to come in. It's not always obvious. It depends on which point you pick, where your clockwise and counterclockwise are. So what I'm doing, I'm forgetting the fact now that's a teeter. It doesn't really matter whether it's a teeter-totter. If I just have this generic diagram right here, and I hold this point stationary and let this stick right here, teeter-totter, twist either counterclockwise around this way or clockwise around this way, around point D. It's kind of like the spinner in a game where you spin the spinner, or the hands on the clock, where this is the center of the clock, and where the hand is fastened down, pinned down, but then this is like the second hand. This red horizontal line is the second hand, and it can spin clockwise or counterclockwise. We don't want it to spin, but we have to think about what if it did spin? What if it did rotate? So what force is here relative to point D? And once again, any force, I haven't said it explicitly, but hopefully you've caught on by now, that any force that's on that point does not create torque on that point, because its distance from that point is 0. This 280 Newton force does not create torque on point D. Only these 3 forces do. That was also true. I erased this. Well, in the diving board problem, only the forces that are beyond the reference point create torque. Okay, so here we go. Which forces create clockwise torque? Well, it's just Fn. And we know Fn is 1100. It's going to push up and try to make this thing rotate clockwise. So Fn is the clockwise. It's going to be 1100 times its distance, which we don't know. We'll call that R2. Equals, that's creating clockwise torque, equals, now there's 2 forces generating counterclockwise torque. There's the 450 the 450, trying to make this thing rotate counterclockwise, times the 1.5 meters plus the 380, that's at 3.0 meters. That's very important, 3.0 meters, because I'm measuring from everything from point D. From point D to C is 1.5, from D to A is 3.0. Okay, and now it's pretty easy algebra. All the physics is done. You get 1100 R sub 2 equals, whatever, 450, oh boy, 680 plus 680, all right, 680 plus another 1100. All right, so then if you do the math, you add those together, you get 1100 R2 equals, you got to round it off to say like 700, so 1800. I round it off a little bit, so R2 is 1.6 meters. In other words, the question says, I think it's the answer, where will this teeter-totter balance? In other words, you have to put this fulcrum, okay, closer to the heavier person. That fulcrum is 1.6 meters from the lighter person, 1.4 meters from the heavier person. So 1.6 meters from smaller person. Always good to put that. Or you could say 1.6 meters from the smaller person, 1.4 meters from the larger person. That's where this will balance. If you put this fulcrum in the dead center and the people who sat there, the heavier person would go down, the lighter person would go up. Okay, let's do a couple more here. Here's a good one, medical example. All right, so here, all right, they're talking about, and you guys, you know, all you bio and pre-med people have a, you know, will have a better understanding of this problem. You have the arm. What is the name of all those arm bones and hand bones? But basically, you're looking at the person's arm here, the horizontal part, the arm plus the hand. All right, they kind of drew it out for you already down here. So this bar right here represents the person's arm. All right, I'm going to redraw that over here on the right. So there's the person's arm, and then because I usually stop my drawing where the forces are, but the hand does extend further than, well, I kind of do their same diagram, but I'm going to put the numbers on here. For example here, and they use these hash marks here to represent that these forces are bigger. They're not to scale, but they're bigger than they're actually drawn here. We don't know what they are, but we're trying to figure out the forces on the person's elbow and the bicep muscle to hold that book steady in stable equilibrium. So I'm going to put the numbers on here. Let me do that, and then I'll come back. So I drew this out and used their numbers. This horizontal red line represents the person's arm. At the end here, there's a 4 kilogram physics book. So, excuse me, that's a weight of 40 newtons. Let's make that 2 sig figs. It came out to be 40 newtons. All right, you don't need to put a little line over the 0, but that I'm saying that's 40. The arm itself, so the CG, says CG here. That's the weight of the arm. That includes all the muscle and skin and bone and the hand bones. That represents the entire weight of this arm, not the bicep part, only this horizontal part of the arm from the elbow to the tips of the metatarsals or whatever they are in the finger. Sorry if I'm messing that up because I'm a little rusty on my biology. And hopefully you guys know these bones. So this hopefully makes more sense to you as far as from the biological standpoint. The physics, though, we're learning. Okay. The weight of this arm, 25 newtons, 2.5 kilograms. Put the total weight right there at that location. It tells you the location relative to your elbow. This is supposed to be the force of the elbow. It's a little bit like the diving board problem, where the forces are very similar in nature, where the elbow has to be pushing down on that arm bone, and your bicep is pulling up, attached with ligaments, or what, you know, I guess that's how they attach to bones. That has to pull up. So your bicep. So what's the force of your bicep? How much force does your bicep have to exert on your arm to keep this steady state equilibrium? So from point A, Clockwise torque equals counterclockwise torque. So you can pick any point. Once again, this one makes the most sense to pick point A, far left. You can pick any point, but because I know all the distances, so generally I try to pick a point where I know distances. And now we got to find out which forces. There's now, the force of the elbow at point A will give you no torque. Like I said in the previous problem, force elbow, which is down, creates no torque on point A. But the 25 and the 40 are trying to make that thing, make your arm go down, and rotate clockwise. That's probably a little bit easier to understand in this case, that you know your arm would go down, and if you held your elbow steady, that's the pivot point, fulcrum if you may. The arm will rotate clockwise based on each of these two. Your bicep has to pull up to keep it from going down. In other words, to try to pull it up, try to make it go counterclockwise. So the two forces, the 25, it'll be the 25 times its distance from the elbow force, from point E, from point A. That's 16 centimeters. I can do this in centimeters, as long as I stay in centimeters. Or you can make that 0.16 meters if you want. Plus the 40 times its distance from point A, 38. So now I'm doing Newton centimeters. That's okay. As long as you keep everything in centimeters, you can do this in centimeters. Equals the force of the bicep, that's force of B, bicep, times its distance, 4 centimeters, 4.0 centimeters. So I'm going to do the math here. Okay, so I did the math here. This is 400 plus 1500 equals force of bicep times 4.0. 1900 equals force of bicep times 4.0. So force of the bicep is about 480 newtons. I want to say these things right. There's no T in bicep. All right, sorry about that if I'm messing this up. But I also want to fix this. The hand bones, actually the big ones near bones, you know these, but I like to say things right, and hopefully I'm not. The metacarpal bones, the big ones, okay, the bigger ones in your hands, and the smaller ones that are phalanx. Hope I said that right. This is a good review if you've forgotten these things. You probably know these things. The arm, I'm not sure which one. The two in your arm, the ulna and the radius. Then the big one, by your bicep, is the humerus. A bunch of sub things or whatever. I don't know, but those are the main ideas. So I want to make sure hopefully I'm not messing up. Double check those things, because all you biology people obviously probably want to know those things and get them right. Ulna and radius, so these two bones, and then metacarpal, phalanx, and then the humerus. All right, I think I'm close on those. But now the physics, which I'm a little bit better at. I hope. Well, I am. Okay. One thing they didn't ask you to do here, interestingly enough, the bicep force here, F sub B, is about 12 times the weight of the book. It's got a lot of force it has to exert, because it's got such a short distance from the pivot point. We could also figure out force sub E. Didn't have you do that. Oh, well, actually, I'm having you do that. So if you do F net equals 0, let me write this down. And then the other condition for equilibrium, F net 0, up and down, the forces up equal to forces down. So the up force is only the bicep force, 480, and then the forces down, the weight of the arm, the weight of the book, and the force of the elbow comes out to 2 sig figs, 410 newtons down. All right, so that's a good physics problem applied to biology and the human anatomy. Next problem we have, a center of gravity problem. All right, looks like a lot going on here. There kind of is. All right, so this one is just, there's somebody balancing a bunch of food on a stick. So once again, we're doing a horizontal problem. The next one will have an angle with it as well. But you could, once again, the starting problem could be a vertical problem, and you got to do everything left and right, but it doesn't matter. Horizontal problem. Here we have, let me draw it all out. So I've done some preliminary work here. It turns out this is going to be a pretty easy problem. Basically, it's asking where this thing balances. So we have this meter stick, and we have an apple, 1 Newton, an orange, 2 newtons, the center of gravity of the meter stick, so that's the weight of the meter stick is 3 newtons, or the stick, whatever it is, and then the loaf of bread. And we know where they're all located. Now I'm going to put those numbers on a diagram. These locations, they have them over here. I'll put them on my diagram in a minute here. But the first thing we can notice is that, okay, the hand is balancing the system. So when you put your finger there, your hand there, your hand is balancing the whole system at the center of gravity of the system. This spot right here where the 3 newtons is represents the weight of the stick. That's the center of gravity of the stick only. All right? It's not the center of gravity of the system. The center of gravity of the system can be supported and balanced if you put your balancing fulcrum, your finger in this case, at that spot. They will all be balanced here. So that's F. Now, this is not in the right proportions because the easiest thing to start with in this problem is the condition for F net equals 0. The up forces equal to down forces. So there's only one up force, the finger, as pushing up the whole thing. So it's just 1 plus 2 plus 3 plus 7. It's 13 newtons up. And now we will do the second condition for equilibrium, and that's the rotation. And in this case, it turns out that I can pick point A. Point A is at the end of the stick because they gave me all the numbers. Once again, you're trying to, the best point to pick is to pick the point where you know all the distances. A lot of times I want to pick a spot where the force is so I can get rid of that force. But here, like if I pick point A to be where this apple is, then the apple would not be part of my next calculation. But in this case, since I know every distance from point A, I'm going to use point A at the end of this stick. Let's do that. Okay, so I did the math here. The numbers in this diagram in blue are the same ones from the original diagram. And they gave me all the numbers, all the distances. I'm going to assume they're all 2 sig figs, even though they're written as a 1 sig fig number. So the apple, the orange, okay, if you hold point A fixed, all of these 1, 2, 3, and 7 Newton forces are all trying to make the thing rotate clockwise relative to point A. And then the force F, the 13 Newton force, is trying to hold it up relative to point A, making it turn counterclockwise if it could turn, but we don't want to turn it, we just want to hold it steady. All right? So it's pretty straightforward. 1 Newton apple times the 10 centimeters plus the 2 Newton orange times its 30 centimeters from point A, everything from point A, plus the 3 Newtons weight of the board times its distance from point A, 40 centimeters, plus the 70 Newtons, loaf of bread, 7 Newtons times the 70 centimeters. Once again, you can do these in centimeters. As long as you stay in centimeters, the answer comes out in centimeters. Or you can convert to meters and put it all in meters and convert back to centimeters. You don't have to. It's just easier to leave it all in centimeters. Just stay, as long as you stay consistent, whatever units you're using, it stays in those units. And then equals the 13 times r, the distance that you're looking for. And then it's just simple math. 10 plus 60 plus 120 plus 490 is 680. Divide by 13, you get 52 centimeters. So the center of gravity of the system is where it balances. That's an important concept. Things balance at their center of gravity. So the finger here is at the center of gravity of the system, 52 centimeters from the left end of the measuring stick. All right, one more. Here's a good one. Let's do this one. So what's a little bit different about this one is there's an angle involved. There's a wire holding up a beam. Sometimes they call it a boom. The boom itself weighs 120 pounds. And the weight of this sign, this physics sign, is 260 pounds. And we can leave this in pounds. Once again, if all the forces are in pounds, they stay in pounds. We don't need to convert. I'll do that in this case. That's the one thing nice about torque problems. If everything's in inches, you can leave it in inches, and the answer comes out in inches. If everything's in feet, leave it in feet, comes out in feet. If everything's in pounds for forces, comes out in pounds, as long as you keep everything in that unit for those particular quantities. Now, what's difficult about this is there's a wire here, all right, that has a tightness we call T, tension in a wire, T, at an angle theta. All right, at the wall here where this beam is attached, we're assuming it's a horizontal beam. All right, there's always 2 components to that force. There's the Y component. I'm going to call this F sub Y. When I get going on this, I don't like it. Well, I'm going to call this F sub Y. All right, and then they call this N down here. All right, I'm going to call this F sub X. Those are 2 components of an actual force. So I'm going to get rid of the N. I'm going to put a dot around. So I'm getting rid of the N. I'm going to call it F sub X. You can call it N if you want. and you can call the upward force F. But those are really two components of an overall force right there. I'm going to put those together to get the resulting force F. That's what the question is asking about in part B. Part A is asking for the tension in the wire. So this is the first problem that we have, that it's at angles. All right, so I've redrawn the diagram over here on the right. So this horizontal red line represents our lever. It weighs 120 pounds, dead center. The sign at the end, the physics sign, is 260 pounds. Like I say, we're going to leave this in pounds. Here's the angle. I actually calculated that angle because I gave you the geometry down here. The wire, it's 5.3 meters long. I think I mentioned that this is a right angle. The beam is horizontal. It's perpendicular to the wall. This is 3.8 meters long. And then so cosine of theta is 3.8 over 5.3. Inverse cosine function on your calculator, 44 degrees. That's important here because now we have an angle that's not 90 degrees. So we've been not putting in the sine of 90 and all those other problems we did. We didn't put that in, didn't have to put that in. Okay. So make sure I have all those numbers correct. I'm trying to get the other thing I want to mention is over here. This is a little bit difficult. At this dot right here, where this thing hits the wall, these are two components of a force. Once again, they call them N and F. But there's F sub Y, but this is F sub X. It's kind of hard to draw here, but it's a force that's perpendicular to the wall along the line of the beam. So we'll come back to that, but it's part of our diagram here. I could, right now, but I'll do it later, I could take T and break it up into two components, which I will have to do eventually. But I don't need to do that yet because the torque equation can factor that in. So I'm going to do my first condition, or one of my conditions for torque. Well, let's call this point A right here. I think we'll use our torque from point A. All right. So from point A, you're going to have your clockwise torque equals your counterclockwise torque. Now, the nice thing about picking point A is we know the distances, like this 120 is halfway. It's half of 3.8 is 1.9 meters. It says that in the problem, how long the beam is. This is 1.9 meters. And this is then also, so that weight of the board is dead center. It's a geometrically symmetrical object. So the total length of the board is 3.8 meters. So I know all the distances from point A. And if I pick point A as my reference point for torque, neither F sub Y or F sub X generate any torque on that spot because they are from that spot. Their force is applied to that spot, so their distance is zero, so there's no torque. So what's going to happen here is the 120 pounds, if this is a rotation spot, which is a little bit easier to see in this case, if this wire were cut. If this wire were cut, this whole board would fall down and rotate clockwise based on those two forces pulling down. The wire is pulling counterclockwise, kind of like the wrench problem we get at the very beginning of these notes, or in part A of the notes. So we have two forces creating clockwise torque, and in one force, counterclockwise torque. Let me draw that out. So from point A, clockwise torque equals counterclockwise torque. Clockwise torque will be the 120 force at a distance of 120 pounds times 1.9 meters, or is it feet? Doesn't really matter. Does it give me feet? It's meters, but as long as everything's in meters, good. So 230 plus then the 260 times the 3.8 is 990. Add those together, get 1210. And I left off the sine of 90. Once again, we've been not putting in the sine of 90, sine of 90. Those are all 90-degree angles. But then, so you got to be careful over here on the right-hand side, counterclockwise. It's T, the force, the tension in the wire, times its distance from point A, 3.8, times the sine of 44. So now we have to remember to put that in. And then if you take the sine of 44, which is a decimal number, times 3.8, you get 2.6. All right? Then you add these two numbers, 1210. Divided by 2.6, you get a tension of 470 newtons. That's the answer to part A of the problem. Okay, so now it gets interesting. We have to apply the other condition for equilibrium to get the F sub Y and F sub X. And one of those things we have to think about is now taking T and finding its components. I'll do that at the top up here. So I've done that. Up here at the top, we found out from our previous part that the tension T is 470 newtons. And the angle is 44 degrees. So our vector component diagram, which we've done several times, t sub x is to the left, t sub y is up. Using cosine of 44, we get t sub x is 340, and then using sine, didn't show the work for that, but that's okay, even on a test. Just give me the two numbers here, show the work once, show the diagram. T sub y is 330. So how does that now help me get f sub y and f sub x? Well, now we use our condition for linear equilibrium. I'll need to erase a few things, so I'm going to give myself some space here. So you might want to pause and write everything down if you haven't. I'm going to erase a few things and add a few things. All right, so the main thing is I've erased some things and now I've redrawn the diagram. So here's the thing. It's the same diagram except for one change in the diagram is I got rid of t, and I never put t and components on the same diagram. I always put my component diagram as a separate diagram, t with its components. Because on this free body force diagram, which applies to torque and linear motion, I have my two components for t, not t. They are substituting for t. So I've got the 330 t sub y, which I calculated right there, t 330, and t sub x is 340. So I still have the 260 down, the 120 down, and maybe you can start to see this. So far over here on the left, I have to have my condition for equilibrium. F net has to be 0. All the forces have to balance. All the down forces have to balance the up forces. Well, now I have two forces up, F sub y and 330, and two downs. So let me fill in the math here on the, over here. So I've done the math over here. Up forces F sub y plus the T sub y, 330, equals the down forces, the 120 plus the 260. That's 380, subtract the 330. You get the y component. This right here is 50 pounds of force. Left and right, so there's only two forces. One's to the left, one's to the right. The 340 is to the left. So, I should have had these. So T sub x is the left. Doesn't really matter here. But these two are equal. F sub x is 340. F sub x is to the right. And T sub x is to the left. So I could have switched these two words. Doesn't matter. They're equal forces. F net of 0. They cancel out in the F net sense. They're equal in magnitude to each other, cancel out. But the last question is, I want to know what F is. Those are the components of F. So my last thing to do is to draw a component diagram. I'll go way to the top again. All right. And you draw a component diagram for my two components. If you have space at the bottom, do it. But I'm going to draw the two components on there and figure out what F is. It says to find the magnitude of the force over here using these two components. So let me do that. All right, so way up here at the top, I drew my vector component diagrams. I always draw those separate. All right, and I didn't draw it to scale because F sub y is 50 and F sub x is 340. So that should be much longer. I should do this much shorter, but it doesn't matter. I'm not going to mark off points for not having this to scale. I mean, you should try to do that, but I want to draw it big enough so you can see it. But this is just straightforward Pythagorean theorem. F squared is the hypotenuse equals 50 squared plus 340 squared. Because F sub y is so small, to 2 sig figs, F comes out to be like 343 or 344, but the 2 sig figs, it rounds down back to 340. So sorry about that, but that's just how it is to the 2 sig figs, because the 50 is so small compared to the 340. F is really not that much bigger than its own component. If you put a 3 sig fig answer here, like 343 or 344, I would give it to you, 344 pounds. Even though you should really stick to 2 sig figs. But there we go. Equilibrium, static equilibrium. The torques have to balance, clockwise, counterclockwise, and the up and down forces have to balance, the left and right forces have to balance to give you no acceleration linearly or rotationally. Up next in the next chapter is rotational acceleration, so stay tuned for that, Unit 10.